Now this is one problem which we can solve. So dy by dx, so here the independent variable is x, the dependent variable is y, and you have the right hand side. So this is a function of x comma y. So if you want to replace x by t, you can do that. If you like to have t and y, you can do that, right? So we have to be ready to work with different symbols, etc. They should not burden us. So in any case, so we have dy by dx is equal to a function of x comma y. And the initial condition for y is given to be 2 because this is a first order ODE. Therefore, you require only one condition to solve the problem. Now what they ask you to demonstrate is find the value of y at x is equal to 1. We know the value of y at x is equal to 0. So they ask us to use a step size of h is equal to 1 to go from 0 to 1 directly, just to demonstrate the idea. So you can come to the answer in several ways. All right. So kindly work on this as I just outlined when I described this set of calculations for you. Okay, so we can use RK4 ideas on this to demonstrate that we have understood the sequence of calculations. So first find out K1, then K2, then K3, then K4, and then yn plus 1. Now here the way I have chosen to do it is to first of all convert this problem into a standard form. We have already discussed this in an earlier exercise, so I will not repeat it. This has been considered in a previous video. So kindly take a look at how this becomes this in terms of new symbols y1 and y2. Basically, I have defined y1 to be y and y2 to be x. So doing that will lead us to this particular case. Now what I do is I write f1. f1 is a function of y1 and y2. In general, f2 can be a function of y1 and y2, but here f2 is just 1. f1 is a little more complex. It is indeed a function of y1 and y2. So we can write out expressions for y1, 1 and y2, 1 because there are two components y1 and y2 and you have to find both of them at x is equal to 1. Alright, we know the value of y1 at x is equal to 0. So the initial condition for y, which is y1, is given to be 2. And we know the initial value for x is 0. So this is the initial value for y2. This is the initial value for y1 at x is equal to 0. Then this is the RK4 formula for y1. This is the RK4 formula for y2. So k1, so 1 by 6, you recognize that. We had k1 plus 2k2 plus 2k3 plus k4. But now we have to look at k11 because the second subscript is for y1. So we have k1, k2, k3, k4 for y1 and we have k1, k2, k3, k4 for y2. So once you get k11, k21, k31, k41, k12, k22, k32 and k42, you would be able to calculate y11 and y21. So these are the sequence of calculations. So K1 for Y1 is going to be H multiplied by F1 evaluated at Tn, Yn. H is 1 and F1 is 4 e to the power of 0.8 times Y2 minus 0.5 Y1. So what is the value of Y at the base point, at the starting point? Y2 is 0 and Y1 is 2. That is what is given in the problem. Y1 is 2 at x is equal to 0 and Y2 is 0 at x is equal to 0. So wherever you see Y1 put 2 and wherever you see Y2 put 0. So when you do that, K11 evaluates to 3. And K12 is H multiplied by F2 evaluated at Tn, Yn. But F2 is always 1 in this particular problem. Look at this. F2, which is the right hand side of dy2 by dx, that's always 1. And therefore, F2 is 1. So K12 is just going to be H. And H is 1 in this case. So K12 is equal to 1. Now, we have gotten K11 and K12 already. So we have got the K1 values for Y1 and Y2 now. K11 is 3 and K12 is 1. Now we use these two values to get K21 and K22. So how do we get K21? We go back here. So right here, we are going to have K21 is going to be h multiplied by function 1 because this is for y1. So we are going to use f1 evaluated at tn plus h by 2, comma yn plus k1 by 2. All right. So what is tn? Tn is 0. H is 1. So this is f1 at t is equal to half, comma yn plus k1 by 2. So yn was 2 and 0, right? y1 was 2 at x is equal to 0 and y2 was 0 at x is equal to 0. To that, you're going to add half of k11, k12. So 3 and 1. So this is k1 vector comprising of k11 and k12. So half 1 by 2 of k1, but k1 is a vector now because there are two components here. So this is going to be 2 plus 3 by 2, which is going to be 5 by 2. And for y2, it is going to be 0 plus half, which is half. So you're going to evaluate f1 at t is equal to half, and y1 is equal to 5 by 2, and y2 is equal to half. So f1 is a function of only y1 and y2. It is not a function of time. Therefore, this half doesn't matter. The time doesn't matter. So wherever you see y1, put 5 by 2. So that's what has been done here. Wherever you see y2, put half. So half. So you get K21 to be 4.2173. K22, right? If you write an expression, it's going to be h multiplied by f2 evaluated at some value of t and some value of y. But interestingly, this f2 function is 1. Therefore, K22 is going to be just h multiplied by 1, which is h, and h also happens to be 1 in this example. So K22 is going to be equal to 1. So we have found out K21 and K22. That means we have found out the K2 vector, which is going to be 4.2173 and 1 respectively. K1 vector was 3 and 1. K2 vector is this. Now you can find out K3 vector. That means you can find out K31 and K32 using a similar idea. I'll leave those calculations to you, but if you do it, you are going to find that K31 is this and K32 is this. That means K3 vector is going to be 3.913 and 1. Likewise, if you proceed, you can find out K4 vector with K41 being 5.9457 and K42 being 1. So we have got all the 8 components: K11, K12, then K21, K22, then K31, K32, then K41, K42. All the values that you get there, you just put it in these expressions that we saw. You're going to get the values for y1 and y2 at x is equal to 1. So that's how you calculate. Now, if you're given other values of h, or if you're asked to find out the values of y at other values of x, you can proceed likewise and get it. So you can understand the kind of pain that we have to go through in doing these computations. So that is when you will appreciate coding, right? And a tool like MATLAB, which programs all these things internally so that we do not have to worry about all this bookkeeping, all these notation, etc., etc. So the same problem, if I have to solve it in MATLAB, I'm going to solve it from x is equal to 0 all the way till x is equal to 4 using a step size of h is equal to 1. So this is dy by dx, a first order ODE. This is the right hand side. So this is a function of x comma y. This is the initial condition for y. So I want to find out the values of y at x is equal to 1, at x is equal to 2, x is equal to 3, and x is equal to 4. That means the step size is 1. So this is the MATLAB code a very simple piece of code that can help solve this problem. So I'm just going to use ODE45. So ODE45 implements the Runge Kutta method, right? RK45, it is sometimes called RK45 method. All right, so RK4 method is used under ODE45, and basically you use the three input arguments. So you will have a ODE descriptor file. So my ODE is the name of the function file that I'm going to use later. So my ODE, right? Then comma the values of the independent variable, right? The domain. So 0 is my starting value of x, and then I want to go in steps of 1. I want to go till x is equal to 4. So this is the values of x at which I want to find out the solution. And this is the initial condition. Because it's an initial value problem, I know y at x is equal to 0 is given as 2. So this is the initial condition. So you have to enter it in this particular order, and the outputs will be stored in t and y. These are the two variables. T will contain the values of the independent variable, and y will contain the values of the dependent variable. So this is a single line of code, and all you have to do now is in the same M file at the bottom implement this function or write out this function. So function space within square brackets f is equal to my ODE, the same name that you gave here, right? So ignore that at when you write the function file here. So here it should be at myode, and here it should just be myode. This is part of the name, and this should be the same. Then brackets open, the symbol for the independent variable, comma, the symbol for the dependent variable, right? I've just used t here, but you can call t or x, that's fine. So you can even replace it by x. So if you replace this by x, you should replace this by x, right? So just be consistent, that's all. And f, right, which is the right hand side of the ODE, is given by this. So 4 times exp of 0.8 times the independent variable, which I've called as t here. If you use x here, you can also use x here, no problem, right? Brackets close, minus 0.5 times y. So whatever is there, which is fed into my ODE, should feature inside as well. And whatever is the variable here should be reflected here. All right, and you end that function with end command. So you put all these things in this file, which I've labeled as ODE demo1.m, and you run that file, you will get this output. So these are the values of x, this particular column. These are the values of y at those corresponding values of x. So the initial condition is when you start off at x is equal to 0, you have y is equal to 2. That's what is given in the problem. And at x is equal to 1, you've got y to be 6.1946. At x is equal to 2, this method computes y to be 14.8439, etc. So this is how ODE45 can very quickly solve this problem for us for y at x is equal to 1, 2, 3, and 4 very quickly. Doing it by hand, we got the value of y at x is equal to 1 to be 6.2010, which is not very different from what we have got here. All right. Please note that when we were doing it by hand, there were several truncations and rounding offs, etc. So we have got this particular result. All right. But if you do it using ODE45, you get a pretty close answer to what we got by hand. But this is expected to be more accurate because we don't have any calculator round offs and things like that. I'll stop here and I'll catch up with you in the next video.